You want. Just keep going.
You definitely ramble a lot. So, okay. So I'll remind you what we talked about last time and kind of give you the context of why we did that. So the last time we constructed this map, this defect anomaly map that goes from the anomalies on our row defect. Our row defects are d minus k dimensional, they're codimension k. So their anomaly class lives in what higher dimension. This describes the invertible TQFT associated with that anomaly. And they have symmetry G, some structure S, which gets twisted by both the original twist that we're studying eta, as well as the representation rho that we've studied. And this goes to bulk anomaly, which is also for G and structure S, but with this twist eta. And so we found for U1 symmetric direct fermion 3 plus 1d. Well, so the anomaly class of this lives in omega 5. Now the U1 spin with no twist, so I just leave it out. Now this group has two Z's, which I'll describe in terms of the 6D classes. So there was the class that we studied, C1 cubed over 6, I believe. This is the one with 6, and the other one is the one with 8, plus a Z class, C1 cubed. And the thing mapping into this is the anomaly of our row defect, which has two space-time dimensions. So this is a omega 3. And the structure we had for that is spin C because of this extra twisting that happens. Okay, this, we also have a Z plus Z. The term that we studied was C1 squared over 8 minus 1 over 24 P1. But there's also a C1 squared term. And so we found that, well, we found that this generator maps to this one by our calculation. Actually, a much easier calculation that you can do as an exercise is that the other generator maps to the other generator there. So this is actually a very simple isomorphism. Well, I guess they get swaps. Well, whatever. It's an isomorphism. And what this tells you, this general theory, so this map is defined so that if you compute this map applied to the anomaly of the row defect, get the bulk anomaly. So this is our anomaly matching equation, and this map is linear. So if you have something non-zero, if you have some theory with an anomaly, and you form the row defect, it has to have some anomaly, because the image of that under this map has to be non-zero. So this has to be non-zero. And so, well, in this case of this free fermion problem, we could exactly compute this localized mode. We did it in the 1 plus 1d example, but you could do it in this example as well, and exactly find the chiral mode with this anomaly associated with like the winding mass vortex of the 3 plus 1d direct fermion. And that's all well and good, but say you add interactions to that problem, you're no longer in the world of free fermions where you just have to think about solving the Dirac equation. The basic index theory no longer applies. And in fact, you can make very wild changes to the theory, so long as you preserve the anomaly, so long as you don't break the U1 symmetry, you're always going to have an anomaly on the row defect. So you can do wild things to this theory. You can add more fields, you can add gauge fields, tons of interactions, as long as you don't touch this anomaly. So this applies, for instance, in the standard model, we have chiral fermions, we have chiral direct fermions, and we have Weyl fermions. And there's some, this equation will apply to them so that if you have a row defect, so in that context, these things are called cosmic strings, that they will also have these localized modes, even though the standard model has all these complicated interactions and gauge fields and so on. This sort of anomaly analysis still applies. Okay. So now what we want to do is understand. So in this case, it's an isomorphism, but more generally, we might ask, is this always an isomorphism? Well, the answer to that is going to be no. So the question I'll instead ask is, what are kernel and image of this map? Now, this is a very physical question. So, for instance, the kernel could be non-zero because this map goes from the defect to the bulk. So it's possible that you can have different kinds of defects. So we'll talk about some examples of those that are associated with the same representation, same symmetry class, but which have different anomalies. But they both match this equation. So their anomaly is going to differ by some lower dimensional anomaly in the kernel of this map. So that will be interesting to understand. And the other thing is, this given a bulk anomaly, there might not be a defect anomaly associated to it. And so this anomaly matching equation must break down somehow. And the way it breaks down is that the row defect itself is not really a local theory in codimension K. So that will be related to this obstruction of row gapability that you need to define a local defect. Okay, so we're going to do that, but to get there, I want to talk about non-trivial families. QFT. So we're going to need some extra tools beyond just the kinds of anomalies that we're used to studying. We're going to need some kind of family anomalies, some kind of anomalies in your space of couplings. So studying QFT and families is a really nice thing to do. It's very natural because we have QFTs come with parameters, and you can think about those as parameterizing a family for every choice of the parameters. We have a QFT. We're used to thinking about RG flow as some flow in the space of parameters. So this is a very natural idea for us, and it's also a very natural idea from the point of view of TQFT. We can study families of invertible TQFTs. It's a very mathematically natural thing to do. So let me give you another interesting. Let me give you an interesting family that also comes from free fermions. So this question is very much related to phase diagrams. So here's an interesting phase diagram. So if we have our 1 + 1d direct fermion, and then we add to it our two mass terms. So there's a psi bar psi mass, and there's a psi, and there's a chiral mass. I think we can differ by I. Then the phase diagram. So if we plot this, what this theory does is a function of A and B. Well, when A and B are 0, that's the theory I'm starting with, which is this massless point. This is a gapless theory. But for any non-zero value of A and B, A or B, we have a gapped theory. So actually out here, and that gap theory has a unique ground state. So the phase diagram is actually featureless, except for this point in the middle. So this is all what we might call trivial phase. So we have some isolated point where the gap closes, and a natural question you could ask is this point necessary, protected? Right? Say we deform this a little bit, we add some interactions. Will this point remain? What will happen to it? Could it just completely disappear? So actually, so with U1 symmetry, so the usual charge conservation for this fermion, it is protected. In the sense that, well, what this point is could change, but you could never completely get rid of it and have a trivial phase everywhere. And the reason for that is that if you think about a loop around this, so we want to measure some kind of winding number. So if we look at this loop, so this is an S1 family of essentially trivial theories. But nonetheless, this family itself can be non-trivial, even though the fibers are all trivial. The fibers are sort of one-dimensional. And actually, that's what happens in this system. So if you think about, so every point on this circle represents a choice of system parameters. So what you can imagine doing is slowly varying those system parameters going around the circle. Imagine that you're varying parameters and you're going around the circle. Now, you can do that. There's a sense in which you can do that slowly because there's an energy gap here. So you can do that very slowly relative to the gap. And there's a nice limit where you do it infinitely slowly. That's this adiabatic limit. And what you see in the adiabatic limit is that this is a one-dimensional system in space. As you're varying this parameter, there's actually a very small U1 current across the system. So this current is roughly equal to the variation of this angle theta on this circle, such that once you go around 2 pi, the time integrated current, so that's the total charge that passes through some point, is exactly 1 charge. So 1 charge, say this gets pumped across the system. So this thing is called ballast pump. And the fact that charge is quantized tells you that this is a non-trivial cycle in in the space of U1 symmetric theories. So we're using this U1 charge, right? So U1 symmetric trivial theories. Because this integer is quantized. So imagine there were nothing in the middle. Then you could continuously shrink this loop. And now as you do that, because the charge is quantized, you're still always going to be pumping 1 charge. But eventually the loop has no area and you're not varying system parameters at all. So how can you pump any charge? That's a contradiction. So that's why there must be some kind of feature here that prevents you from collapsing this loop. Indeed, if you think that this is essentially a slice in the space of theories, this is a non-trivial loop in the stratum of the trivial phase of the space of U1 symmetric theories. So it is protected. I mean, you can deform this in various interesting ways. You can change this, but you'll always have something there. So this is also, this ballast pump, by the way, is related to a bunch of other interesting things, especially in condensed matter physics. Laughlin related it to the quantization of the Hall conductivity in the quantum Hall effect. It's also related to this Lieb-Schultz-Mattis theorem. It's like very simple proof of that theorem by Oshikawa. And so I want to advocate that this is analogous to Berry phase. Maybe you're familiar with this fact that suppose we study a two-state system with a Hamiltonian just in terms of Pauli matrices. So up to an overall shift, the most general 2x2 Hamiltonian looks like this, the most general 2x2 Hermitian matrix. For there to be a degeneracy in this spectrum, all three of these A, B, and C have to be 0. So in the phase diagram, at A equals B equals C equals 0, you have a twofold degeneracy. And everywhere else in 3 dimensions, you have what we might call a turbulent phase. There's a single degenerate state. But you can't get rid of this point, right? Because if you look at the line bundle on the sphere linking this point associated to that unique state, so the subline bundle of this overall trivial bundle, that has term number 1, which tells you that you can't get rid of this point. So I like the name that these have from optics. They call them diabolical points. So in the same sense, I want to call this a diabolical point of quantum field theory. So if you're thinking about this in a 3-dimensional band structure, by the way, this is the sort of thing that you have in the Weyl semimetal. The dispersion of your fermions look like the Weyl equation near one of these. As you can see from this looks just like the Weyl equation if you linearize it. So the fact that this is codimension 3 has some interesting physical consequences. So that's a pretty large codimension. So it means that if you just tune a single parameter in a quantum system and you look at what the energy levels do, they don't really cross each other. They tend to just have these near misses. They tend to get close and sort of bounce off of each other. If you're just tuning one parameter, you don't expect to ever actually hit one of these doubly degenerate points. So this is this phenomenon known as level repulsion. It's also a feature of the random matrix distribution, why it's very different from like Poisson distribution and so on. That's because these points occur in codimension 3. So even just in quantum mechanics, it's very interesting. If you add symmetries, you can reduce the codimension. For instance, say you have the U1 symmetry, which is rotation around the z-axis, then that'll set A and B to 0. So then you'll only need to tune one term, the C term, to get a crossing. So that's more analogous to this, where you have codimension 2 now. It tends to be that as you go up in space dimension, you go up that many dimensions. You go up that many codimension to find these diabolical points. But in QFD, there's also systems with, so QFD also has non-trivial families without symmetry. For instance, with Anton and Poshan, we studied this Abanov-Wiegmann family. So these are nice because they're free fermion examples, but an extremely budget example that you can have in mind So in 1+1 DCFT, we have this SU2 level 1 theory. So this is a special value of the radius of a free scalar that has actually SO4 symmetry because it has SU2 left and SU2 right. And if we add to this theory our SO4 vector, so the lightest SO4 vector, then you get, this will break all of the symmetries once we add this vector. And we'll get a trivial theory for any non-zero value. So you get this picture where you have the SU2 level 1 point at the origin, and in all other dimensions, in all other points of this 4-dimensional space, you just have a trivial theory. And surrounding this is an S3. And what you can think of is this S3 is like, so SU2 is an S3 itself. If you're thinking in terms of like the WDW field theory for this point, then what we've done is we've just chosen some point of SU2 and pinned the value of the field to be that point. That's what the sort of infinite field limit looks like. So if you think about now to study this, we look at effective field theory for a map from our 2D spacetime X into this S3. So this will be essentially a topological theory where we have background, we're allowing this perturbation to vary in space and time and studying the effective field theory that we get. And you can just see that the Wess-Zumino-Witten term of this SU2 level 1, this effective field theory will include this Wess-Zumino-Witten term at level 1, which has a quantized coefficient. And it's that quantization which is preventing you from getting rid of this point. Because if you had nothing there, then you would be able to shrink the S3, and you would have to conclude that the Wess-Zumino-Witten level was 0. So we called this higher Berry phase. Because it's like a higher dimensional generalization of this Berry phase example. But yeah, it's essentially these Wess-Zumino-Witten type terms. Well, there's a way to organize this. So we can generalize our cobordism theory to include phi. So what we want, so we're going to study this. These are going to be cobordism invariants of, well, cobordism invariance in this, with this caveat that it fits into the universal coefficient sequence is what we mean. So these are cobordism invariants of E manifolds X with there's the G gauge bundle, there's the S structure that we had before, and now the extra thing is a map from X into the parameter space. And so this is going to classify metric families of invertible theories. So for example, this Thales pump, so that's essentially coming from group cohomology. So we can use, whatever, I'll just write this. So we have omega-3, E1, SO of S1. Now what this is, you always have when you have a sphere here, you can split this into a part that doesn't depend on S1. So that's not the part that we're interested in. So these are sort of constant families over this S1, where you just have some three-dimensional theory that you've chosen for each point. Plus, now using the spectrum property, omega 2 U1 SO. So this is the lower dimensional thing. This is the thing that gets pumped. Sorry, this should be 2. We're talking about 1 plus 1. Thing that gets pumped is a 1 lower dimensional thing in the case of S1 family. So this happens to be Z. That was our charge that gets pumped. Now, in terms of effective actions, so we're talking essentially about effective actions that we can write that are functions of the gauge field as well as this parameter map phi. So our effective action for the thallus pump is simply going to be, so it's an integral over our two-dimensional space-time, A d phi over 2 pi. Well, let me write it as e to the is so you understand my normalization. It'll be e to the I A pi over 2 pi. So I'm thinking of phi as 2 pi periodic, so that this is an integer winding number. And you can see if you were to compute the current, the U1 current by varying with respect to A, you'd find exactly this. Well, I guess it was theta here. So you would find that Jx is d2 phi over 2 pi by varying with respect to A. And so indeed, this topological term corresponds to this thallus pump phenomenon. And so you could equivalently think about this quantization as the quantization of the coefficient of this term, which is guaranteed by, say, large gauge transformations of A. So just like the quantization of Chern-Simons terms.
Well, apparently this example has nothing to do with did you have fermions, since it also works with.
Oh yeah, here I wrote bosons. Right. It's a right. So for fermions, we could write it as well. So in this case, we would have the U1 that acts here is a spin C. We have spin C of S1. Well, so in this case, the omega 2 spin C is 0. So we only get this pump, and that's also a C. So it has the same interpretation of the U1 charge, just with the caveat that the U1 is extended by the fermion parity. So yeah, it's actually a single fermion that gets pumped across. Yeah, good question. So many of the phenomena are occur for both bosons and fermions. There's a map from spin cobordism invariance to oriented cobordism invariance, right? Where you sort of just forget about the spin structure on your manifolds. Sorry, that would go from oriented cobordism invariance to am I right?
Map from spin to SOs for invariance, it goes in the other.
It goes the other way. So you have a map from oriented invariance to spin invariance. Right, those are the ones you just forget. Yeah, they don't depend on the spin. So there's a lot of similar phenomena that you see between bosons and fermions. Now, family anomalies, they occur at the boundary of these non-trivial families. So what do these look like? Essentially, when you have a non-trivial family, or when you have any sort of family, what you can try to do is choose a boundary condition for that family. So similar to how, what a boundary condition for that family means is that for every parameter value, we want to have a boundary condition. And it could depend on the parameter value, but if it does depend, then it has to depend continuously. So it has to respect the periodicity, or it could perhaps not depend. Maybe you can choose a boundary condition that works for all of the families, something like that. All parameter values of the family. Now, analogous to how when you have a non-trivial G-symmetric not family, but just theory, you can't find a G-symmetric invertible boundary condition. So likewise here, if the family is non-trivial, you're not going to be able to define a invertible boundary condition of the whole family. So let me demonstrate that with our Thales pump example. So if we think about the Thales pump now with a boundary, so it's a one-dimensional system. Yes.
Can I ask about the credit part of the lecture? The idea is you have a field that depends on capital, so promote the parameters to fields. The adiabatic limit means that you neglect the kinetic terms of these fields. They vary so slowly that you can forget about them.
Well, you can do a sort of derivative expansion.
Yeah. And then, but in order to preserve the symmetry, you have to assign charges to these fields. And what you just discussed is some sort of a mixed anomaly, or is it you couple these fields to the backgrounds for your symmetry, no? But they can have an anomaly. Like in that case, the term would shape background with invariance.
So here there's no anomaly, but so this is a two-dimensional theory with a two-dimensional term. This is just some quantized term in the effective action for those fields. So we're doing some kind of derivative expansion and looking for quantized terms that appear. So if you have a background gauge field, say in this example, you have a term that already appears at first order in derivatives of phi.
Yes.
But if you don't have a symmetry, say we do this Westamina-Witten example, that appears at third order in derivatives in phi. So yeah, we're just looking for these quantized terms because those are going to be topological invariants of the family. They're going to be the things that protect these diabolical points. Now, in the case of anomalies, we're going to be thinking about the boundary of this term. And there you could think about the gauge variation with respect to A produces some kind of interesting boundary term that depends on the parameter field. So that's kind of where the family anomaly is coming from. But let me just give you the physical picture of this. So in the Thales pump, as you go around a cycle, you pump one charge across the system. Well, if we have boundary, the charge has to get stuck there. We have to have charge. Charge accumulates here. So what that means is that in any boundary condition, if you go around 2 pi, now our boundary condition must have changed because there's more charge here. So it can't be the boundary condition that we had before. So what happens is, so we're calling this, so I'm calling the parameter field phi, but if we have a constant parameter, let me think about it as phi constant to be theta running from 0 to 2 pi. So essentially, there's going to be a special point. So how to say it? We can almost choose a non-degenerate boundary condition for the whole family, but there will have to be a point let me just draw it. So here we have our bulk diabolical point. Where the fermion is massless. And it's in some two-dimensional phase diagram. There's going to be, now, if we also draw what happens to the boundary, so here we'll have a unique ground state for the bulk plus boundary system. And here we're going to have a boundary level crossing. So at theta equals pi, what happens is here we have a state of, let's say, charge Q, and there's going to be some other state near it of probably this charge Q. Give me some other state of charge Q plus 1 that has more energy, but at theta equals pi, they're going to cross in energy. So that when you're done, it looks like the charge has increased by 1. Now, what happens in this system with the bulk is that you have the bulk spectrum here. So this is the bulk gap, which never closes. But there will be some place where these states join the continuum of the bulk, and they in fact delocalize. So there's some tone here where you have two localized states. Their degenerate energy, two states localized to the boundary, they're degenerate in energy along this point, and then there's some place where you don't see any ground state phase transition, but that next excited state delocalizes. So this is maybe an academic point about quantum systems. I mean, there's a version of this for the Berry phase. So the anomaly associated with the quantum mechanical Berry phase is simply that you can't choose the ground state of that Hamiltonian smoothly over the entire sphere. So it's like not having a boundary because you can't choose an initial state over the entire sphere. But let me give you a more impressive application of this. So let's study 1 plus 1D QED with a U1 gauge field with n charge 1 bosons. So this is sometimes called the CPN -1 model. So it has a theta angle, because it's a two-dimensional theory, so we have this term, theta integral of F. And it also has some global symmetries. So it has this, well, there's a UN that acts on these bosons, but because there's a gauge symmetry, that actually becomes PSUN once you mod out by the gauge group. We have this flavor symmetry. And for n even, there's an anomaly, the PSUN anomaly at theta equals pi. I should say the reference for this is our paper with Fedor Shron, Shinanjo, and Zohar Komagrodsky. So n even, there's an anomaly at theta equals pi, and that anomaly is associated with this class. So what is the anomaly? The anomaly is PSUN 1, which is Zn. So when n is even, we take the generator of the Z2 subgroup as our anomaly. That's associated with this class. You can roughly write it as E. Actually, let me write it. Use this one. Let me use this one with Z coefficients. Zn. So this is the integer class. So it's an n torsion integer class. So I can look at e to the I pi u3. And so this is the anomaly. So it implies that there's some kind of phase transition that happens at theta equals pi. And indeed, you can understand that from this theory in various ways. But for n odd, this class looks trivial. So n odd, you still have this class, but now n is odd. So n, when n is odd, 2 is invertible mod n. So you can find a k so that 2k is 1 mod n, and this gives you a counter term. So U3 comes from a Z mod n class in degree 2 called U2. So you can express a counter term. So 2D counter term, k times U2 over n. And since k is essentially like a half mod n, when you take the derivative of this, plug in this formula, you get something that's transforming in the same way as this. So it's it cancels the anomaly. So from the point of view of the anomaly, it's just an even n thing. But actually for odd n, we still observe a phase transition. And the interesting thing is that if you study this counter term in the context of the family, what this counter term does, you can see it has the gauge variation of this U3. If we just add this counter term to the whole family, what we've essentially done is we fixed the gauge anomaly at theta equals pi, but we put it at theta equals 0. We put the anomaly at theta equals 0. So all we did was move it from theta equals 0 to theta equals pi. And it turns out you can't get rid of it because you can't turn this k into a continuous coefficient that would be able to match theta. So there's no choice of the counter term over the whole family. So this is the first family anomaly we encountered. So this is family anomaly we'd write will be a 3D term, d phi over 2 pi. So that's degree 1 times the U2. So this is depending on the PSUN gauge field. And right, with 1 over n here. So this anomaly, so this is a class now in this sort of homology. This makes sense for any n, even or odd. So these family anomalies really give you results that you can't derive just by thinking about ordinary symmetry anomalies. So another interesting example of this phenomenon, there's a really great paper called Theta Time Reversal and Temperature that's about similar dependence on the theta angle for QCD-like theories with either some kind of interesting non-simply connected flavor symmetry or some center symmetry, where there's likewise if n is even, you have anomaly at theta equals pi. They didn't know it at the time, but later work of that Lam and Clay Cordova and Dan Fried, they found that also Natty Seiberg, they found that you could also relax the condition and being even or odd. So you get the same story essentially, where instead of U2, you just write this like Pontryagin square, this like 4-dimensional term that you have associated with the QCD anomaly. And so they called that anomalies in the space of coupling constants, but I think family anomaly is less of a mouthful, so I prefer that. But it's logically the same thing. Okay.
All the way back.
Yes.
And so it's a 1+1 B theory that you're considering here, and you're considering this S1 family as a background field with target S1 here, and in that picture, so in that picture, the boundaries are your 0+1D theory that's on the boundary. But I don't quite understand how like what does it mean for the charge to accumulate here? What that means in terms of the picture that you drew before the pumping.
So this is a picture of space. So, and think about varying the parameter slowly. Then we have this current. So the charge is going to the right. So at the end of a 2 pi cycle, you're gonna have one more charge here and one less charge here because one charge gets pumped across. So that's what I mean, charge accumulates. So you have to go from a state of charge Q, whatever you had before, to charge Q+1. And I'm saying that the only way that can happen is for the spectrum to do something like this, where you have your state of charge Q. This is at theta equals 0. So I'm thinking about constant in space parameters varying slowly in time. Now this, I'm actually not even thinking about it varying in time. This is just the spectrum at every constant value of theta. So as you crank this up, you know, at some point this state Q has to be replaced of charge Q has to be replaced with a state of charge Q+1. So there has to be some place that they cross. Now, they don't have to cross at theta equals pi. I chose a particularly symmetric. If you choose some other boundary condition, then this thing could wiggle all around, or you could have even more features in the boundary phase diagram. You know, lots of interesting things could happen, but this is a sort of minimal one. The minimal thing is always that the bulk diabolical point is the end of some kind of diabolical locus at the boundary. You can relate this also to SPT edge modes. So there's charge conjugation symmetry in this problem. Yeah, if you impose charge conjugation, what happens is that the vertical direction in this phase diagram is odd under the symmetry. So your actual symmetric phase diagram would just lie along this axis, and then you would see that this is like a trivial phase still, but this is an SPT now for the extra symmetry. So you can think about this bulk diabolical point as coming from as just being that SPT edge mode, these two states whose charge differs by 1. So yeah, these things are kind of all connected, but I think that the point of view of the higher Berry phase is cool because all of the like symmetry stuff kind of descends from it. I mean, you could think about things like an SPT is an invertible family over BG, that kind of thing. So this is like a very natural generalization. Everything that we're used to studying. Well, I should say at least it's a generalization of everything we're used to studying with invertible symmetries. I don't know, you know, what the related generalization would be for categorical symmetry, directed spaces or something like that. Okay. So now going back to our problem of studying symmetry breaking. So our idea is to study the explicit symmetry breaking family. Get over let's say a big sphere. It's still centered around the origin. S rho inside our representation rho. So what I mean is we have our symmetry breaking operators. They transform in this representation rho. For every point on this sphere, we just choose that value for the symmetry breaking. And we think about the theory that we have there. and we think about how that family varies over the sphere where they all have the same magnitude. So we're almost able to do this. I mean, we're almost able to apply our theory, except that we want G in the game, right? And the problem is G is broken. G acts on the sphere because it's broken. Well, as long as rho contains anything but the trivial representation, then G is going to act non-trivially on the sphere. So actually what this is, it's not a family of symmetric theories anymore. What we actually get is what I want to call a G equivariant S rho. So this is, you could consider this not just for the sphere S rho, but you can consider it for any space that has a G action. It's a really useful generalization of a symmetric family. You can think about, well, here we have an example. For instance, if we have this charge conjugation, then this is no longer symmetric for that charge conjugation because it's acting in this direction. So that's like, looks like trivial plus sign. Well, it's an equivariant family in the sense that the theory here, if you apply the symmetry to that theory, you get the theory here. So you're getting sort of exact duality mappings for the elements of G that are not in the stabilizer of your point, whereas elements that are in the stabilizer of the point are acting as symmetries. So this is a way to talk about both symmetries and dualities on the same footing, as well as to talk about families where we've broken the symmetry, but we still want to remember how the symmetry is acting. So we can also classify these with cobordism. So let's say we have an invertible the equivariant. Of invertible theories. So here M is some space dx. So we'll typically want it to be the sphere in the representation space. But let's just say it's some space. Well, an interesting thing that doesn't happen in the symmetric case is that even though every theory is invertible, G could still be anomalous. So this happens actually, for instance, in this Dallas bump example again. So you have so not for this charge conjugation symmetry, but for the axial U1, which is broken by this mass term. So that acts by rotation in this space. That has the chiral anomaly coming from, the axial and the vector together. So the vector symmetry, the U1 is everywhere, so it doesn't act. And they share an anomaly at the center point. And even though we've broken the axial symmetry, the anomaly is still there when we think about the equivariant family. So actually those anomalous families are not easily classified for the Bordism theory, but let's say we have, because we basically cannot study consistent couplings to G gauge fields. So we need to assume that this is anomaly free. And then in this case, this is the same thing as just a single invertible T2FT. for manifolds X equipped with. So we need a G gauge bundle. G gauge field. Okay. Some kind of S structure. Possibly twisted. So we study the same sorts of twists. So twists just defined in terms of the G action. And well, I would want to say that we have a map. We almost want to say that we have a map X to M, except that this would not play well with gauge transformations because G is supposed to act on M. What we really want, so we have X, we have sitting over X, the G gauge bundle. We can associate to that a bundle whose fiber is M. So our parameter map is actually going to be a section of this bundle. So this is like our map phi that we had before. So you can sort of think about this as the family version of gauging, or spurion analysis. You know, we promoted our parameters to fields, and now we can just think of a single theory that has those fields in it.
The same as doing like a sigma model with an orbifold target. At least it looks like.
Yeah, it is the same. It is the same because this data, basically the classifying space for the G bundle together with this section is the homotopic quotient to them. So yeah, you could even package phi and A together as a map to M mod mod G. Sometimes that's useful. So yeah, if you're thinking about M mod mod G as like the orbifold stack, then it's the sigma model into that.
Twisting in this combined way, like given that you have another vector bundle.
So this twisting, so we have the gauge field. So I'm thinking about I have an S structure on Tx plus A star of eta. Psi is my structure. So that's the structure on this. I could consider more general twists coming from vector bundles on the homotopy quotient, right? That's sort of involved in phi as well. So yeah, I could include those. I won't need to for the defect anomaly story, but yeah, those could be interesting for other reasons.
You know, the twist on G induces a twist on the homotopy quotient.
Yeah, exactly, because we have this map. Right, this is essentially the universal M bundle over BG that we're pulling back here. Right, very cool. So the whole diagram, maybe if you want, is that we have X, G, we have M mod mod G over here. This is a pullback square, which means that this section is the same thing as the lift of this map. So you can encode everything that way too. Right, so this equality, it's kind of interesting that you can turn a family of theories into a single theory. Mathematically, you can think about this as a conclusion of the cobordism hypothesis, because you have a sort of map from M into your space of dualizable objects, and then you can just put that into the tangent structures that define your TQFT, and just think about that's a TQFT for manifold with a map to M. And then you just have to think about how to include G, and then you'll get the story with the homotopy quotient. So yeah, this. So we're going to write this also as an abelian group with the same notation. So this is going to be, these are d-dimensional. Then we're going to write it in the same notation that we were using for symmetric families, where we remember that G acts on M as part of the data defining this. So in the last lecture, we'll study some of these guys and show how it allows you to compute the kernel and the image of the defect map. Yeah, I think that's a good place to stop.